Welcome everybody. Today we are going to talk about the combinational logic design from the course of embedded system. Combinational logic is the basic building block of any embedded or computational system. It makes all the arithmetic operations possible. Transistor is a basic electronic component of digital system, and this can be used as a basic block for building the combinational logic. So the importance of transistors can be in various ways. It can act as a simple on-off switch circuits that invert the gate input, which is usually called as inverter, can be built using two basic transistors. Also, the circuit whose output is logic 1 with at least one of its input is logic 0, or a circuit whose output is logic 1 with both of its input are logic 0 can also be built using the transistors. These circuits are shown in the figure. So, as it can be seen, the gate input is the input to the transistor. By controlling the gate input, the transistor can act as the switch which is on and pass all the current from source to drain and conducts if gate is equal to plus 5 volt. Similarly, if the input to the gate is 0 volt, the transistor acts as the off switch and does not conduct for the input voltage which is 0. In the figure B, we can see the PMOS transistors for the input of the gate which is equal to 0. In figure C, the transistors, which is a pair of transistors used, act as the inverter. That is, when the input to X is 1, the output at F will be 0. Similarly, if the input at X is 0, the output at F will be 1. The transistors can act also like the NAND gate or the NOR gate, which is given in figure D and E. NAND gate and NOR gate are the universal gates of the digital logic. So in short, if we want to define a combinational circuit, it is nothing but a digital circuit whose output is purely a function of current inputs. Such a circuit will not have any memory of the past inputs. Well, the steps to design a combinational circuit using our basic logic gates. The basic logic gates includes the inverter, AND, NOT, NAND and NOR. So the first step to design is to describe the problem, that is the problem description. In this, the description of the output in terms of input needs to be done. The second step includes translate that description to a truth table. Truth table is nothing but all possible combinations of the input values needs to be written on the left and the desired output values needs to be written on the right. Later, go ahead with the derivation of the output equation for each and every output variable. Minimize the number of logic gates in the circuit. This minimization can happen by algebraically manipulating the equations which are obtained for the output, or alternatively by using the K-map, that is the Karnaugh maps. Hence, the step 5 is draw the circuit diagram. In these steps, we can design a combination circuit for any simple or a complex problem description. So as seen in the figure, for the combination logic design, the problem description is defined in the block A. Here, the output is Y and Z with the input A, B and C. So the problem describes as the output Y is 1 if A is equal to 1 or B and C is equal to 1, and Z is 1 if B or C is equal to 1 but not both. So based on this problem description, a truth table need to be written where the inputs are on the left and the output on the right hand side. The output for the input 3 can be not more than 8, that is 2 raised to 3, which is equal to 8. So all possible combinations of the inputs A, B and C can be 0, 0, 0, 0, 0, 1 and so on till 1, 1, 1. The output for the respective input are written on the right hand side. So according to the problem where it says that the output Y is 1 if A is equal to 1 or B and C is equal to 1. So as we can see in the first row where the inputs are 0, 0, 0, the output is for Y is equal to 0 because the input A is 0 and the B and C, that is 0 and 0, is equal to 0 again. So both the conditions give the output for Y equal to 0, whereas the output for Z is also 0 because B or C is equal to 1. Here none of the B or C is equal to 1, so output for Z is also equal to 0. In this way we can derive the output for all possible input combinations according to our problem description. Once the output and input are written in the truth table, the output equations need to be derived. The output Y can be written as A dash BC plus AB dash C dash plus AB dash C plus ABC dash plus ABC. In a simple way, like we can consider all possible outputs and we just need to describe it in terms of the input. So the minimized output equations can happen by doing the computational adjustments or by the use of the K-maps. Here they have shown a simple example for this problem description in the K-map. Once a K-map is obtained and the output equations are obtained, we can draw the respective diagram of the circuit and the circuit can be implemented. So these are the basic steps for the combinational logic design. Although we can design all combinational circuits in this manner, large circuits would be very complex to design. For example, a circuit which has 16 inputs would have 216 or 64K rows in the truth table. One way to reduce the complexity is to use components that are more abstract than logic gates. These components can be multiplexers, decoders, comparators, or anything. The figure shows few combinational components. This includes the n-bit m cross 1 multiplexer, where the input to the multiplexer is n bit and the output is selected according to the select lines from the inputs which is given. There is log n by n decoder, which is the reverse of the multiplexer. There is n bit adder, which can add and produce the output in sum and carry for all the input bits from A, B and so on. N-bit comparator. The n-bit comparator compares between the input bits, input signals, and produce the output, that is, it is less than or equal to or greater than. N-bit M function ALU, which can perform the operations like arithmetic, subtraction, addition, multiplication. So in this way, these combinational components which are more abstract can be used and the complex design can be simplified. Thank you.